Welcome to the next module of this ionic polymerization. Now, if you recall that previously we discussed about the cationic polymerization of carbon-carbon double bond. In this head, we discussed about the various initiation protocol for this cationic polymerization. We discussed about the photo initiation effect. We discussed about the radiation induced initiation steps, etc. Now, in this particular chapter, we will discuss about the propagation, chain transfer and termination and the kinetics of cationic polymerization. So, because this particular lecture deliberated more towards the basic mechanism of this cationic polymerization. So, let us have a look about this propagation step. Now, in the propagation step, the initiator ion pair usually consisting of carbocations and its negative counter ions. So, these two things counter ions they produced usually in the initiation step, with the example of, say, if you recall in the previous lecture we discussed about the boron tetrafluoride. In continuation process, if you recall that we discussed a lot of various techniques for this initiation step. Now, this further proceed to propagate by a successive addition of monomer molecules. So, let us have a look about this particular aspect. CH2C this which we developed during the course of our initiation process, and CH2 double bond CH2, this may gives you HCH2 C CH3 CH2 C CH3 twice BF3OH. So, this facilitates the further propagation of these things, or sometimes in a very short form, if we would like to refer, that it may be represented as IZ plus M. Now, this is the more appropriate form to represent in the reaction engineering concepts. So, when we try to develop the reaction mechanism, then it facilitates the things. If we talk about this particular addition process, usually it is by the insertion of monomer between the carbocation and its negative counter ion, as discussed in the previous reaction. Now, sometimes isomerization, polymerization need to be addressed. Now, the propagation reaction, this can be complicated in some cases by the occurrence of intramolecular rearrangement, because it is a suo moto habit of all these polymer chains for this intramolecular rearrangement. So, the polymerization proceeding with rearrangements, they are referred to as the isomerization and polymerization, and when we need to address this issue, one must be very selective in this approach. The extensive rearrangement during the propagation usually occurs for a variety of alkenes, usually referred as alpha olefins. The best examples are propene, 1-butene, and higher alkenes. Sometimes they yield to oligomers with highly irregular structures due to the various combinations of hydride or methide shifts. So, the propagating secondary carbocations, they are insufficiently stable to propagate without extensive rearrangements. Simultaneously, only oligomers they are formed, since none of the rearrangement pathways are favorable for rapid propagation. So, the extent of rearrangement during cationic propagation usually will depend on different factors. One factor is the relative stabilities of propagating and rearranged carbocations and the relative rates of propagation and rearrangements. Now, these both factors, they favor the propagation without rearrangement of for monomers like styrene, indene, and sometimes chemorone, vinyl ethers, isobutylene, etc. Now, this is one of the structures of styrene, indene, isobutylene. You can see over here. Now, these are the structures which are equally important when we try to develop the rearrangement patterns under the edges of isomerization of those polymeric species or the under polymerization process. Now, not only these monomers propagate via reasonably stable carbocations such as tertiary, benzyl, oxycarbocations. The carbocations have no routes available for rearrangement to more stable carbocations. So, it is a very, you can say, the tedious type of a situation. Now, isomerization, polymerization yield high molecular weight products. So, when reaction proceeds further through a relatively simple rearrangements route involving stable carbocations. Now, when we talk about the chain transfer and termination, various reactions sometimes led to the termination of chain growth in cationic polymerization reaction. Now, see, these two things, the chain transfer and termination, both are equally important compared to the propagation. The reason is that whenever you require the polymer to have a desired property, then you need to truncate the polymerization at appropriate time and appropriate juncture. So, that is why this chain transfer, sometimes you may transfer the charge, sometimes you may transfer the radicals, and by any means you need to terminate the things. So, that is why this particular concept is extremely important to address. Now, many of the reactions, those who terminate the growth of a propagating chain, sometimes they do not, sometimes they do. So, the termination kinetics chain or termination kinetics need to be addressed properly. Now, terminate the kinetic chain, sometimes there may be formation of a new propagating species is generated in the process, and sometimes it is quite advantageous, sometimes it is disadvantageous. Now, the disadvantageous may sometimes it may promote to the formation of other polymeric chains. Those polymeric chains sometimes may not be desired one. So, these propagating species sometimes referred as the beta proton transfer. Now, the transfer of a beta proton from a propagating carbocation is the most important chain breaking reaction, and that decides sometimes the property of the polymer. Now, it occurs readily because most of or much of the positive charge of the cationic propagating center resides not on the carbon, but on the beta hydrogen because of the hyperconjugation. We have already discussed this hyperconjugation concept. Now, monomer counter ion or any other basic species in the reaction mixture can abstract the beta proton. The chain transfer to monomer sometimes involved the transfer of a beta proton to monomer with the formation of terminal unsaturation in the polymer. Now, let us have a look about some mechanism of this chain transfer and termination. Now, let us see this particular chemical reaction. CH3 hold twice and CH2. See, now this is the positively charged CH3, and I am referring the previous examples in this reaction. Now, this is CH2 double bond C CH3 twice. This may give this CH3 C plus BF3OH negatively charged plus H. It is bonded with the CH2, CH3, CH2 plus H, CH2, C, CH3 whole twice, CH3 whole twice. Now sometimes for the ease of explaining the mechanism, we may refer to this like H Mn plus Iz plus reacts with monomer. This is the termination or transfer rate constant. This may be Mn plus 1 plus H M plus Iz minus. So this is the basic mechanism of this chain transfer and termination. Now there are two different type of beta protons and two different type of unsaturated end groups. Now these are possible for if you take the example of isobutylene as well as some other monomers such as indene or alpha methylstyrene, etc. Now the relative amount of two end groups depend on the counter ion, identity of the propagating center and other reaction conditions, because sometimes during the designing of the reactor or sometimes during the designing of a reaction mechanism, this particular information is quite important. So because people may interested to have the knowledge about the relative amount of these two end groups. So that depends on the identity of propagating center and other reaction conditions apart from the counter ion. So only one type of unsaturated end group, that is referred as internal group, is possible for other monomers such as styrene, ethyl vinyl ether, etc. Now it should be pointed out at this juncture that the kinetic chain is not terminated by this reaction, since the new propagating species is already generated and it is equally active in the reaction mass. So therefore it is not being terminated. You can't say that there is being terminated. Now chain transfer to monomer is on much more favorable term with the propagation in many cationic polymerization compared to the radical polymerization. Now since it is kinetically indistinguishable from the propagation, the relative rate of transfer and propagation usually given by the ratio of usually KTR m upon Kp, this KTR m upon Kp, which is the chain transfer constant for monomer Cm. The value of Cm usually, this is referred as equal to the Cm, the value of Cm determines the molecular weight of the polymer if other chain breaking processes are not significant. So again your molecular weight distribution plays a vital role. Now the larger the value of Cm, the lower will be the molecular weight. It is quite obvious to this particular mathematical equation. Now chain transfer to monomer is the principal reaction that limits the polymer molecular weight for most monomer, especially at reaction temperature higher than say about 20 degrees Celsius. Now since the chain transfer to monomer generally has a higher activation energy than propagation, it is usually suppressed by working at a low reaction temperature. Now chain transfer to monomer reaction involving the hydride ion transfer from monomer to the propagating center for the case of boron trifluoride is referred as HCH2C CH3 CH2C BF3OH minus plus CH2 double bond C CH3 whole twice, then CH2C CH3 CH2 BF3OH plus H CH2C CH3 then CH2CH CH3 whole twice. So this is the basic reaction. Now chain transfer to counter ion involves now chain transfer to counter ion. This involves the transfer of beta proton to the counter ion. Now the initiator and co-initiator is regenerated by its expulsion from the propagating species, and as in the chain transfer to monomer, the polymer molecule has a terminal double bond. So it can be represented like this: CH3 whole and now CH2C plus. You see over here that this is BF3OH2 plus H CH2C So this is the you can say sometimes referred as spontaneous termination. When we talk about the spontaneous termination, sometimes we may say that if it is in the more generic term, like we can represent as H M N M plus IZ, Mn plus 1 plus H plus IZ minus. Now the chain transfer to counter ion usually differs kinetically in that the rate of chain transfer to monomer has a first order dependency on monomer, while chain transfer to counter ion is zero order in monomer. Now, when we talk about the chain transfer to monomer, this is usually the dominant termination reaction compared to the chain transfer to counter ion. Now, when we talk about the chain transfer to beta proton or to other basic substances in the reaction mixture, it is quite evident that it also possible. The various beta proton transfer reaction, they limit the polymer molecular weight, but do not terminate the kinetic chain. Now let us have a look about the combination with the counter ion, because we discussed about the importance of this counter ion. Now termination by a combination of the propagating center with the counter ion occurs like HMN M plus IZ. We can write this one. And the rate constant for the termination is given by Kt Hmn Miz. Now alternatively, the propagating ion may combine with an anionic fragments from the counter ion. Now the termination by the combination, sometimes this differ from the other modes of termination in that particular kinetics which we discussed. Now this chain is usually terminated since the counter ion of the initiator co-initiator complex, it decreases. At last, when we discuss about the chain transfer to polymer, now there are several chain transfer to polymer reactions are possible in cationic polymerization. The transfer of cationic propagating center This can occur either by the electrophilic aromatic substitution or hydride transfer. Now, intramolecular, when we talk about the intramolecular electrophilic aromatic substance, or sometimes if you recall that we refer to it as a backbiting, when it occurs in the polymerization of styrene, so it may affect the other aromatic monomer with the formation of terminal endenyl structure and the regeneration of sometimes regeneration of initiator co-initiator complex. So, we have discussed the various modes of termination. Now, let us have a look about the other modes of termination. Now, various transfer agents they are present in the solvent or impurity or deliberately added to the reaction system. They can terminate the growing polymer chain by transfer of a negative fragments of any kind of radicals, etc., sometimes referred as A negative. Now, this HM M plus Iz minus sometimes may react with the Xz to give HM Ma plus X plus Iz. Now, water, alcohol, acid, sometimes anhydrides and esters, they have a varying chain transfer properties. The presence of any other or any of these transfer agent in the sufficient concentration sometimes results in reaction, which we showed in this particular slide, becoming the dominant mode of termination. Now, termination by these compounds sometimes involve the transfer of HO or RO or RCOO anion to the propagating carbocations. Aromatic ether and alkyl halides are relatively weak chain transfer agents. Now, transfer to the aromatics occur by alkylation of the aromatic ring. Although a chain transfer agent usually decreases the degree of polymerization in proportion to its concentration, it is not expected to affect the polymerization rate, since initiator co-initiator complex should be regenerated on transfer. Sometimes one finds that the more active transfer agents like water, alcohol and acid, they do decrease the polymerization rate. That is, they function as inhibitors or retarders, etc. So, the decrease in the polymerization rate is usually caused by inactivation of a co-initiator by reaction with the chain transfer agent. Now, sometimes we will talk about the examples. So, other example of chain inhibitors, retarders are like amines, triaryl or trialkyl phosphines, thiophene, these are or benzoquinone, etc. These are the other inhibitors or retarders. Now, let us discuss about the kinetics of cationic polymerization. Now, overall kinetics vary considerably, depend largely on the mode of termination in a particular system. Now, we may consider the case of termination exclusively, sometimes by the combination of the propagating centers with the counter ion. Now, here when we talk about the kinetics of cationic polymerization, now the kinetic scheme of initiation, propagation and termination usually consist of say Ri is equal to K At I Zy M, you may refer as equation number 1. Then rate of propagation, that is Kp Ym plus I Z into m. This may be referred as equation number 2. Then RT, that is the rate of termination, that is KT y m plus IZ. This may be referred as equation number 3. Now, where we may say that this y m plus Iz is the total concentration of all sized propagation centers. So, this may be referred as like this, K ZY, concentration of M upon KT. So, this you may refer as equation number 4. Now, if we combine the equation number 2 and 4, this yields the rate of polymerization as Rp is equal to Ri Kp m upon Kt. This is equal to Ki Kpi Zy m square upon Kt. This may be referred as equation number 5. Now, here the if we talk about the number average degree of polymerization this is obtained as the propagation rate divided by the termination rate. So, this may be mathematically represented as Rp upon Rt is equal to Kp m upon Kt. You may refer this as equation number 6. So, when we talk about this one, the chain breaking, sometimes this involves the chain transfer to monomer or spontaneous termination, and the chain transfer to the chain transfer agent S, sometimes referred as water impurities, etc. In addition to the combination with the counter ion, the concentration of propagating species remain unchanged. So, you may write that the concentration of the propagating species, they remain unchanged. Now, assuming relatively small amount of, you may take assuming small amount of S such that the co-initiator is not inactivated. So, that this we may write that co-initiator not inactivated, sorry. And the polymerization is rate is again you may given by this previous equation number 5. Now, if we talk about the degree of polymerization, usually it is decreased. This degree of polymerization is decreased by these other chain breaking reactions, and usually given by the polymerization rate divided by the sum of chain breaking reactions. So, it is given by the polymerization rate divided by the sum of all chain breaking reactions. So, you can represent this degree of polymerization, this xn, this equal to Rp upon Rt plus Rts plus Rtrs plus Rtrm. You may represent this as equation number 7. Now, here this Rts is equal to Kts y m Iz. This is equation number 8. Then RTRM is equal to KTRM YM. That is equation number 9. Then RTRS, that is KTRS YM plus IZ. This is equation number, you can represent that equation number 10. So if we combine the equation number 3, equations 3, 5 and 7 to 10, all these equations if we combine together, we may get this bar xn is equal to Kp m Kt s plus Kt Rm. Now this may be represented as equation number 11, or sometimes if we try to go for some rearrangement, then it can be given as 1 upon xn, bar xn is equal to Kt upon Kp plus Kts upon Kp plus Cm plus Cs m. This is equation number 12. Now here Cm and Cs are chain transfer constants for monomer and chain transfer agent S, and it is defined by KTRM upon Kp and KTRS upon Kp. So this is Cs and this is Cm. Now for case when chain transfer to S, this terminates the kinetic chain, the polymerization rate is decreased and it is given by Rp is equal to K Kp I Zy m square Kt plus KTRS. Now in the usual situation, the radiolytic reaction, they determines the rate of initiation, and in that case the Ri is given by Igm, where I is the radiation intensity and G is the number of radical cations formed per 100 electron volt of energy absorbed. Now in sufficiently pure system like concentration of water and other terminating agent, or we can say that the concentration is we can say 10 to the power minus 7 to in the range of minus 10. The termination of the propagating carbocation centers occur by the combination of negative fragments. So this is represented as Yi, that is the negative fragment, and Kt, this is My. Now this Y negatively charged is either, you may say that the solvated electron, displaced electrons formed during the radioelectric reaction, it is sometimes referred as Y negatively, or the product of the electron having reacted with some compound in the reaction mass. Now, if this Yi is an electron, the propagating carbocation centers are converted to radical centers, and that subsequently undergo the reaction with some species in the reaction system to form the molecular species. Now, in this, if we talk about the termination rate, so the termination rate is given by RT is equal to KT m plus Y is equal to KT m plus square. Now, here this m plus is equal to Yi. This is due to stoichiometry in the radiolytic reaction. Now, if we set that Ri is equal to RT, and if we combine the result with the equation 2, this yields the polymerization rate. This is our ultimate objective, that what should be the polymerization rate. Then this is represented as Rp is equal to Kp m Ri upon Kt dash to the power half, or Kp m to the power 1.5, then Gi, which is in the usual notation, to the power half. So, this is my polymerization rate. So, by this way we discuss about the kinetics. Now, this particular thing is quite different from other cationic polymerization, in that the polymerization rate is half order in Ri. Now, this half order dependence is same as observed in the radical polymerization. So, for cationic polymerization initiated by radiation in reaction systems, where the major termination occurs by the reaction with some species other than Yi minus, the termination process is first order, not the second order as in the case of termination which we previously discussed, and the termination process in the propagating center and the polymerization rate will show the first order dependency on Ri. So, by this way we discussed the kinetic of cationic polymerization, and in this chapter we gave the emphasis of initiation, propagation and termination, and we developed the polymerization rate equation with the help of several concepts which we discussed in the previous lecture as well as in this lecture. And again, if you wish to have further studies, we have listed these references for your convenience. Thank you very much.